So there's nothing like signing.
It's hard to judge. It's hard to judge.
All right, let's open up to page 97. So last night, I asked you to view a few pages that just went over some more examples of finding a derivative, okay, using that limit, that difference quotient to help us do that. What we're going to take a look at today is another limit. Yes? You want to get it? Yeah. Okay. What we're going to take a look at today is another limit that can help us find a derivative. So it's going to be kind of an alternative limit, okay, a different one. What I need to stress, though, is what I need to stress is that these two limits that we talk about in this particular section are important, but I would say that they're not necessarily essential for finding a derivative. Okay, right now, what you viewed last night was kind of a long, tedious process to eventually get these two equations. Okay, so these were the results from two of the problems from last night. We have to use a limit, we have to use h's and x's, we have to combine like terms, things are going to cancel out, okay? I think you would agree it's kind of a process. We're eventually going to talk about some shortcuts, which I think we all appreciate, okay? But in terms of the limits, we don't necessarily have to know how to apply them, we just have to know what they mean and what they represent. Okay, the actual application of derivatives, those shortcuts, are going to come later. Okay, so I don't want you to think or feel like you have to use that h and k limit every single time. Okay, I would lose my mind if I had to do that, and I'm sure you would too. But shortcuts are kind of in the future. Okay, so last night, this was one of the problems that you took a look at, and after we did the long limit for a derivative, this is what we got as our derivative equation. I then asked you to find some equations of tangent lines. So if you were to plug in -1 into your derivative, notice how the slope of the tangent line was going to be -2. Okay, that's something you looked at last night. What we're going to try to do is take a look at this other limit. And if you take a look at it, it's still a difference quotient. Notice how you're subtracting two outputs up top, and you're subtracting the inputs on the bottom. It's like change in y over change in x, and you're dividing them together. So this is another difference quotient. We're going to see what this will result in when we apply it to these two different functions. So if you take a look at the way it's represented here, notice how now we have a limit with an x approaching something. That's not the h that we saw yesterday. So in this case, we're going to have x approaching -1. Okay, that was the value or the location we were interested in for this previous example. The difference quotient then goes on to tell us that we want to take the original function f of x, okay, which is the beginning equation. So we'll go ahead and write that down. And then we want to subtract f of a. So if you were to plug in this -1 into that equation, what would we get? That's what we want to subtract. So we might have to figure it out for a little bit. If you plug in -1, what do you get? 4. Okay, so up top we have f of x minus f of a. And this is all over x minus a on the bottom, but notice how if we're subtracting -1, that would change to a plus. All right, let's see if we can simplify from here. So if you look at the numerator, -x squared minus 4x, we can do 1 minus 4, which would be -3, all over x plus 1. Now it's still a limit, so we should still try direct substitution first. But if you were to plug in -1 for those x's, what's going to happen? No bueno, 0 over 0, right? Okay, so how can we get around that? Where do you want to go from there? Factor. Okay, so how might the top factor? Well, first of all, we can probably pull out the negative. So then we got to think about two numbers that multiply to positive 3 but add to a positive 4, since those signs are going to switch. X plus 3, x plus 1. Okay? All over x plus 1, so x plus 1's go away. We're left with negative quantity x plus 3. So now if we plug in negative 1, we'll get 2, but the negative out front would be negative 2. What do you notice about our result from this limit? Go ahead, Anush.
It's the slope of the tangent line, not negative.
Okay, so what you did last night is you created a general equation for the derivative. Notice how there's still an x in there. So that means if this is the general equation for a derivative, you can plug in any x value you want. For instance, negative 1. You could plug in 10 if you wanted to. But this limit is still finding a derivative value, but it's specifically at this location. So if you wanted to find another location like 10, you'd have to repeat this process all over again. Do you understand that? Because this is just the value at negative 1. The reason the h and the k limit is so powerful is because it gives you an equation that you can use to quickly identify any value you want. Like plug in negative 1, plug in 10, plug in 5, whatever. Can we see the difference between the two? Okay, they both find the same value. It's just that this one is at this spot, whereas this one is at any spot that you pick. Okay, so sometimes one's better than the other, but to each their own. We're going to try the next one. Okay, so we should probably anticipate a value of 1/6. Let's just see if we can get it. So we're going to use this difference quotient. So x would be approaching 7. Okay, that's the location where we want to find the slope of the tangent line. So we're going to take the original function, and then we got to subtract f of 7. So if you were to plug in 7, you get 3. Yep, square root of 9, we get 3. So on the bottom, we would need x minus a, but notice how our a value is 7. Okay? So by using this difference quotient, do you kind of see how it turns into a limit that we're pretty familiar with? We saw a lot of these in the last unit. Okay, so let's go ahead and see what we can get from there. 0 over 0, unfortunately. So how do you want to rewrite it? Conjugate. All right, let's do that. So square root of x plus 2. This would change to plus 3. And we'll do that on the bottom as well. All right, so multiplying the tops. Just worry about the firsts and the lasts. Do not multiply the bottoms because it would get crazy. What's going to happen? Yep, if you simplify the top, you get x minus 7, so that would cancel with the bottom. 1 over that conjugate that we wrote. So now if we plug in 7 for x, we'll get 1/6. Okay, so notice how we now have another limit that we can use to help us figure out a derivative value. Okay, it's no longer h's and k's, but it's still a difference quotient. Okay, change in y's over change in x's. Okay, whole idea of slope. So we're just going to write down that idea here at the bottom. Okay, what does this limit represent? So this can represent the slope of the tangent line, okay, aka derivative, on the graph of f of x at the one point, okay, x equals a. So this is another way we can figure out a derivative value. But the difference is this answer is only the slope at your A location. Okay, it's not a general equation you can use for anything. So this is not the slope everywhere. This is only the slope at 7. you'd have to go through the whole process again if you wanted to find a different location. So it is another limit value, but whether you use this one or the H one is completely up to you, whether you're finding an equation or a point. Okay, so we're kind of going to bring both of them together, like the differences between the two, on the next page. So this was the main one that we did yesterday, okay, with the H's and K's. We went through the whole picture, like where this comes from. So whenever you use this H limit, this is normally producing a function, okay, something with a variable left in it. So this is a function that represents the slope of the tangent line at any point. Okay, it's at any point because you get to pick the point you want. On the other hand, okay, this difference quotient we just did with the A, okay, no H anymore, this is no longer a function because if you take a look, I'm going to flip it real quick. If you take a look at the two we just did, notice how the answers were not functions. Okay, these were values. So this limit is producing a value that represents the slope of the tangent line at one point, specifically x equals a. So if you're trying to figure out the derivative or the slope of a tangent line at various points, you're probably better off using the H limit because you can plug in any location you want. But if you only need to figure out the derivative or slope at one location, okay, maybe you want to use this one because all the other values don't matter. So they're each strategic, or I would say, what's the word I want to use? Appropriate depending on the particular question or problem, but sometimes one might be easier than the other, okay, depending on the question at hand. So like I said, I think earlier, these are not necessarily necessary. I just used that word twice. These are not necessarily important when we're going to try to figure out the derivative itself. Okay, we just have to be able to recognize these and how they represent a derivative. We're eventually going to get to shortcuts to figure out the function a little bit quicker than using a limit. So what I mean by that is if you look at the examples at the bottom, all of these limits, they kind of look similar to the ones that we did previously, but they're telling us that these limits specifically represent a derivative. So they must fit one of the two limits at the top of the page. Okay, they must fit that format. What we need to be able to do is recognize what function are they applying the limit to, and what is that specific x location of c or a or whatever they want to call it that we want to find the derivative for. Okay, that 1 point on your graph. So we need to think about, is it the H limit, is it the A limit, which one does it fit? If you take a look at the first one, the kind of hint for you is probably what the limit is approaching. Notice how this one is an H limit there. So this function, whatever it is in there, should fit this setup. Okay, we need to try to identify what is that original function. And then, what is the x value that they plugged into that original function? Okay, the x location that we want to find the slope for. So how do you think we can tackle this? Or maybe you can recognize it by just comparing the two of them. What do you think the original function was? So where are you looking to find that? This first piece?
Yeah.
Okay.
I just compared it to the x plus h.
Okay, so notice how the first thing we did in a limit yesterday was we plugged in x plus h for all the x's. So if you take a look at how this first piece is written, notice how we have 2 plus h and 2 plus h So it's probably representing the x plus h we plugged into that. And if this is what you plugged in, it had to have originally been x's in order for you to plug it into that spot. So it looks like we have 5x squared minus x plus 7. So that's our original function. The question is, what is the x value that we are figuring out the derivative for in this specific limit? If it's normally x plus h, what is it here? 2 plus h. Okay, so that's our x value. So this limit, whenever you evaluate it, is basically finding the derivative of this function, okay, the slope of a tangent line, specifically at the x location of 2. Okay, so I'm not saying we have to simplify it, we just have to recognize it. Okay, so we have to know what to look for in the problem itself. Let's go ahead and try B. So if you take a look at this one, notice how it's x approaching a number. So this is that alternative one, that alternative difference quotient with the a in it. So we have to take a look at how this is set up and compare it to what the difference quotient looked like for that derivative limit. Can we identify what the original function is and the location of where we're trying to find the derivative, the slope of that tangent line? What do you think, Anush?
I think the function is 1 over the square root of x squared minus 2x.
All right, and where were you looking to find that?
It's just the first term in the numerator.
The first term. Okay, so notice how in this other limit, f of x is just represented by whatever's written first up top. Okay, that f of x function. So that's what we can write there. What is the location on the graph that we're trying to figure out the slope for? 7. Good, because that's what you're approaching. Okay, that was your a value that you wanted to plug into the derivative. So there's a difference between the two, whether it's an h limit or an x limit. We need to be able to recognize what is the function and where is the point. Okay, I'm not saying you have to simplify them, we just have to recognize them. Do you guys think you can try the rest? Give it a shot. Okay, identify the function and the location. Alright, some are a little harder than others, and most of us look done or almost done, so we'll go ahead and check these out. What about C? Can we identify what the function was that they used for the limit? What are you thinking, Noosh? Tangent of x. Okay, so if you were to plug in x plus h into this, notice how it would kind of look like what they had initially wrote as the first term in the numerator. Okay, so I like that. And then what is the x value that we're trying to find the derivative for? Good, Christian? It is pi over 4 because it's normally x plus h that we plug in, and notice how instead of an x we have a pi over 4. So the pi over 4 took the place of the x. They're exactly the same. I like it. What about D? It's another h limit. So we're looking for that kind of x plus h that we can substitute in. We get e to the x. Okay, so looking at this, if you plug in x plus h for that x, it would look something like that. And notice how instead of x we have pi. What about e? This one was a good one. What do you think, Griffin?
I said natural log of x.
Okay, so normally our difference quotient for the h limit is f of x plus h, so notice how that would fit here, but then you subtract the original function, which would have been f of x. Now, why do we think it's not written there? What do you think, Griffin?
Because you end up plugging in 1 for x,
Uh-huh.
and the natural log of 1 is 0.
0. Okay, so they didn't actually write that extra step there, like you kind of see on the ends of the previous two, because it ends up being 0. So the main thing I would look for is that plus h portion, and that's kind of hinting you for what the original function would have been. That one was tricky. What if we moved on to that a limit, kind of that alternative one? No h's in this one. Can we identify the original function? Go to Noosh.
X minus 2 t.
Perfect. Okay, so that's just the first function that's written, and then what's our x location? Good, Christian?
Is it 5?
It is 5. Yep, whatever the x is approaching. If we check out g, that's another h limit. So we want to find where the x plus h is written. So that looks like it shows up first. So this would be 3 natural log of x. Okay, instead of the 2 plus h, it was originally an x. So if it's normally x plus h, and now it's a 2 plus h, the x value would have been 2. For h, this was not an h limit. Okay, it was an a limit. So f of x is the first function written, and then the x value is whatever we're approaching. How did we do? Pretty good? Okay, so all of these limits represent derivatives, how you're finding the slope of a tangent line, but notice how we're just recognizing what was the function, what is the location. Okay, we're not necessarily solving them. Okay, I would say this is kind of the main idea of this section. We have to be able to do this. Okay? All right. We're going to do more practice with this identifying next week. I do, like when we have our board activities, I do want to move on to the next section though, and I think that this is going to really help this idea of a derivative sink in. Okay, so graphing examples, looking at a picture, most of us are visual learners. So far, what we've said a derivative represents is the slope of a tangent line, okay, drawn on a curve, okay, at a specific point. So what we're going to do is take a look at this curve, and I have different dots labeled on there. We're going to try to estimate the derivative. So we don't really have a function to actually do the whole limit process for. We're essentially just going to try to draw a line and guess what the slope of that line would be. So after we do that, we're going to take a look at the graph, try to determine is it increasing, decreasing, is there a max or a min, and then we'll practice writing those tangent lines that we did yesterday. Okay, so if you go to the x location of -7, which is our first dot, I want you, to the best of your ability, draw a tangent line that would just touch at that spot. Once you have your line, I want you to calculate the slope. What does the rise over run kind of amount to? Everyone's might be different because they're all estimates or they're all hand-drawns, but we should get close to something. Three. Okay, so if I do mine, 1, 2, 3. I had 4. I could understand 3. 6. I could see that too. Might be a stretch, but I can see it. Okay. Remember, these are all estimates because we're hand drawing it. So if it's an estimate, we have to show that on our paper. So for our notation, because we're going to have to get used to how we write this, we're going to have f prime of -7. So the slope, the derivative at -7, is roughly, write down your number. I don't care what it was, 436, okay, whatever. That was your approximation. Okay, but make sure you use that squiggle because it's an approximation. So notice how this is the slope at that point. What is the graph doing at this point? Increasing, decreasing, max or min? Increasing. Okay, and then we're going to practice writing the tangent line equation for this spot. So if you want to write the equation of a line, we need what?
2 points.
That's going to give us a slope. 2 points for a slope. We need 1 point and a slope for a line. Okay, so we know the slope was 4 or 3 or 6, whatever your estimation was. And then the point is coming from the actual spot on the graph. So notice how if we have an x value of -7, our y value was -3. Okay, so point slope form from there, we'll have y plus 3 equals 4 times x plus 7. All right, we doing okay? We're going to go on for all the other points. So let's try the next one. X location of -6. Draw a tangent line to the best of your ability. Calculate rise over run. What was your slope estimate? I got 2. At least that's what mine is. 3 I can understand. Okay. If you get 10, we're doing something wrong, right? Okay. Estimates. What's the graph doing at that spot? Increasing. All right. And then let's practice writing the equation of that tangent line you drew. So our slope was 2. The point on the graph was -6, 0. So we'll put the 2 together in point slope form. So y minus 0, 2 times x plus 6. All right, let's try the next one. -4, tangent line. What's the slope of that spot? 0. Is that an approximation or an actual value? That's actual, so we can throw an equal there. Increasing, decreasing, max, min. Max. All right, and we'll write the equation of that horizontal line. Most of us might be able to go straight to y equals 2, because that's the height of the line. But if you want to actually go through right point slope form, that's okay as well. Okay, horizontal line at the height of 2. That would be fine. Do you guys think you can try the rest of them? Yeah. Remember, they might be estimates, so your slope might be different from your neighbor's. let's check them out. What was your slope at -2, roughly? What do we get? -1, anything else? -1/2, -2. Okay, I got -1 as well. I would say you could be off by like 1 or 2. I'd say it can't be 0 though. Okay, because it's not a flat line. So I'd say -1. Decreasing, right? Graph's going down at that spot. So using the point, you can write your point slope form as long as you have your slope in the correct spot. Okay. What about the slope at -1? Roughly? -2, anything else? -3, that's okay. -1, -4, something like that. I would say that's fine. Decreasing because the graph's going down. So point slope form, make sure you have your slope in the right spot. What about the slope at 1?
0.
Exactly 0, right? So that can be an equal sign. We're at a low point, a minimum. So you could have written point slope form, or since it's a horizontal tangent line, you could have just had y equals -4. Okay, would have worked out to be the same thing. How are we doing so far? Good? Yes.
For -1,
Mm-hmm.
for the point slope formula, would it be y plus 1 because the y value is negative?
Oh, I didn't write that down there. Yeah, so that should be -1 according to the graph, so that would be a +1, right? Good catch. All right, let's check out 3. What was your slope estimate at that spot? 4? 5? I got 3. I mean, we're all close. We got 2. Okay, I got pretty close to 3. So you can be like 2 above, 2 below. Definitely not 0 though. Okay, there are certain values that I think would make more sense than others. So we're increasing at that spot. So we'll put our slope in our point slope form. What about the slope at 5?
0.
Exactly 0. Okay, horizontal tangent line. So you could have written your point slope form, but since it's a horizontal line, maybe you had y equals 4. Okay, either one would have worked. What about at 7? This one was pretty steep. I got -5. -4, -6, something like that. Okay, it's a pretty steep spot. So we're definitely decreasing, and then put your slope in point slope spot. How are we doing? Good? Okay. We're going to leave off there for today. Or on Monday, we're going to take a look at this chart a little further and see what the derivative is telling us about the original function. There might be some patterns in there.